In the first two videos, we will look at how voltage and current are affected in the two types of circuit configurations, series and parallel. We will do this by observing the brightness of the LEDs in the two circuit types. First, we will look at a series circuit where components are connected in a single loop. We have constructed a series circuit with a 220 ohm resistor and two red LEDs. The whole circuit is switched on together and switched off together. This means that if one of the components stop working, there's also a break in the circuit, so electrons cannot flow, so this whole circuit will fail. We will apply a voltage source. You can see that the two LEDs light up with equal brightness. In a parallel circuit, components are connected in separate branches. We've constructed a parallel circuit with two branches and a 220 ohm resistor, and one red LED in each branch. The branches in the circuit can be switched on and off independently. This means that if one of the components in a branch stop working, electrons continue to flow through the other branches, so the circuit will not fail. When we apply a voltage source, you can see that the two LEDs light up with equal brightness and are brighter than the LEDs of the previous series circuit. As more and more LEDs are added in series, they become dimmer, as current flowing through them is reduced. Removing an LED and creating a gap in the circuit causes the other LED to switch off, as no current can flow. As more and more LEDs are added in parallel, brightness does not change, as current only flows through one LED in each branch. Removing an LED and creating a gap in a branch does not affect other LEDs, as current can still flow. We now build a circuit with a 6-volt source and a 220 ohm current limiting resistor, and two red LEDs in series. With the ammeter dial set to a maximum limit of 200 milliamps, we see that the current flowing is 10.7 milliamps. This reading is taken at a point between the resistor and the two LEDs. Now we will remove the ammeter from the circuit, replace it with a lead, and reposition the ammeter between the second LED and the voltage source. An ammeter has very little resistance, and so we place it in series to measure the current flowing through it and the rest of the circuit. The current rule for all circuits is current in is equal to current out. We are testing this rule by measuring the different points in our single loop series circuit where current in is at the battery and current out is at the battery's opposite end. For the rule to hold, the current we measure should be the same at all points in our circuit. Keeping the same setting on the ammeter, it can be seen that it reads 10.6 milliamps. The current is essentially the same for the previous reading, minus the micro losses caused by component heating. Taking the same series circuit, we are now going to measure the voltage across each of the components in the circuit. A voltmeter has a very high resistance, and so we always place it in parallel to the part of the circuit we are measuring a volt drop across. We position the voltmeter parallel across the resistor. Note that the LEDs are shining, which means the circuit is closed with current flowing. The maximum volt rating is set to 10 volts on the voltmeter. We can see that the resistor has a voltage of 2.2 volts across it. Let's connect the voltmeter directly to the power supply now to see how much voltage is actually being supplied to the circuit. On the voltmeter, we can see that the screen reads 6.2 volts. Now reposition the voltmeter to sit in parallel across the first LED. Check that you have wired the circuit correctly. That is, all components sit next to each other in a loop with separate branches on either side of the first LED containing the voltmeter. The voltage rule for series circuits is that voltage across each component should add up to the voltage of the power supply. Applying the power supply, you should see both LEDs light up, and our voltmeter shows a reading of 1.9 volts, which is the voltage drop across the first LED. So far, we have measured a voltage of 2.2 plus 1.9 equals 4.1 volts being used in our circuit. Now reposition the voltmeter to sit in parallel across the second LED. As both red LEDs are from the same package, you should expect to see the same volt drop across the second LED, as they both offer the same resistance to the circuit. Applying the power supply, you should once again see both LEDs light up. Voltmeter now shows a reading across the second LED as being 1.9 volts. Thus the total voltage in the circuit is 6 volts, close to what we measured. So now we set up a circuit so that our two LEDs are in parallel. The orange leads are the one branch of the circuit containing one LED, and the yellow leads are the second branch of the circuit containing the second LED. Remember, the current rule for circuits states that the sum of the currents flowing towards a point in a circuit always equals the sum of the currents flowing away from that point. So now we will measure the current flowing through each branch of the parallel circuit. We will put the ammeter in series with the orange branch first to measure the current flowing through this LED. The ammeter is now connected with a maximum rating of 100 milliamps, and we can see that the current reading is 8.6 milliamps in the orange branch. Now disconnect the ammeter and put it in series in the yellow branch to measure the current flowing through the second LED. Okay, so now we have current flowing through both branches of our circuit. With the ammeter connected in the yellow branch, the current flowing through both branches should be the same, as both branches offer the same resistance. You can see the ammeter reads 7.6 milliamps in the yellow branch, and the negligible difference is probably due to one LED having used more than the other in the past. We will now remove the ammeter and place it in series with the main circuit to test if it equals the sum of the two currents flowing into the branches just measured. We will thus reposition the ammeter next to the power supply and hope to get a reading in the region of 8.6 plus 7.6 equals 16.2 milliamps. This is because the sum of the currents in both branches is the same as the current in the main circuit. That is before and after the circuit splits into two branches, or current in equals current out. Once repositioned, connect the power supply to the circuit and check the two LEDs light up to ensure the circuit is closed. You can see on the ammeter that the total current is 18.8 milliamps, close enough to our estimate. Current losses are probably due to wiring and tiny resistance of the ammeter itself. For our last parallel circuit, we will measure the voltage across each circuit component. In a parallel circuit, each parallel branch has the same voltage across it. For our first measurement, we have connected the voltmeter in parallel with the first branch of the circuit containing one of the LEDs using green and yellow crocodile leads. If we look at the voltmeter to read the volt drop across the LED, we will see that it is 1.9 volts. Our voltmeter is set to a maximum rating of 10 volts. Now we will disconnect the voltmeter to sit in parallel with the second branch of the circuit containing the second LED. We can see that the volt drop across the second LED in the second parallel branch is also 1.9 volts. Now we will measure the voltage across the resistor in the main circuit, positioning the voltmeter so that it is once more in parallel with the component it is measuring. You can see that the voltmeter has been placed in parallel with the resistor connecting the power supply. Once more, we get a reading of 4.1 volts, which is the volt drop across the resistor. Because the two parallel branches have the same voltage across them, total circuit voltage is 4.1 plus 1.9, which is equal to 6 volts. which is the same as our power supply voltage.